exponential growth and decay. If you're given a situation where you have a population of things, maybe number of animals, and you're told that the population grows at a certain percentage each year or minute or some unit of time, then you can use this formula here as its growth formula or to model how fast it's growing. The little b is the initial population, initial amount of things you have, and then t is your unit of time, like years or minutes or seconds. And then this capital A here is the percent rate that it's growing at as a decimal. Now, if your population is decreasing at a certain rate or percentage, then you can use this formula here. So it's the same as the other one, but you do 1 minus capital A instead. So little b again is the initial population, and then capital A is the percent rate that the population is decreasing at, but as a decimal. Little t is the time unit, so that's a variable. Let's look at an example. A population numbers 13,000 organisms initially and decreases by 7.4% each second. Suppose p represents population and t the number of seconds of growth. An exponential model for the population can be written in the form p equals b c to the t. Find p of t. So we're supposed to find this exponential equation to model the situation. So we are told that the population of bacteria is decreasing by 7.4%. So since we're told that it's decreasing, we're going to use the second equation here. So we're going to use this one, which is the one we use when the population is decreasing. So I'm going to copy that down. So our p of t should have the form b times 1 minus a to the t. And we just need to figure out what is b and what is a. T is a variable. It's the time unit that in a can change. Okay, so b in this equation, it's always the initial population. So let's write that down. So b equals initial population. Now we're actually told what this initial population is. We're told that we start with a population of 13,000 organisms. So that's going to be our b. We're told that's the initial amount. So little b is going to be 13,000. What about capital A? Well, capital A is going to be the percentage decrease, but as a decimal. So let's look back up here. We're told that the population decreases by 7.4% each second. So our percentage decrease is 7.4%. So I call this little a, it's 7.4%. Now we can write this percentage as a decimal by moving the decimal place 2 places to the left. So capital A is going to be 0.074. So these two numbers are going to be plugged into our general formula. So I can take the formula for p of t equals b 1 minus a to the t, and I can plug in b is 13,000 and a 0.074. Now if I simplify this a little bit, and in other words, if I subtract right here, I do 1 minus 0.074, I'm going to get an equation in the form that we were supposed to have. Okay, now we were told we wanted an equation of the form b times c to the t. And that's exactly what we end up with. So what is this equation? Well, it gives us the number of bacteria that we'll have if the population of bacteria starts with 13,000 and then we look at any time after 0. So we start the time at 0 seconds and then maybe like 10 seconds later we can plug in 10 and then we would have how many bacteria there are after 10 seconds. I'll show you what I mean with part B. So part B is to estimate the bacteria population after 7 seconds. So we have this formula, P of T equals 13,000 times 0.926 to the 7. Oops, not to the 7, to the T. And we're asked to estimate the bacteria population after 7 seconds. So the way that this equation works is we can plug in 7. So if we plug in T equals 7, it'll tell us what the bacteria population is after 7 seconds. Now you'll need a calculator for this, and what I would recommend is doing 0.926 to the 7 first, then multiply your answer times 13,000. And you're going to have to round. So if we type this into the calculator and round, we're going to get about 7,589.6, or about 7,590 bacteria if we round to the whole bacteria.